Okay, we appear to be recording, are we? Hey, so first, nobody showed up for the SI session today for calculus. But to show you that I have no harshness in my heart toward you for blowing me off for the session today, I'm going to show you something cool. I'm going to show you how you have already been doing implicit differentiation and using the chain rule, and you didn't even realize it. Now, hopefully, it'll help you in the future because once you understand that, maybe it'll help you use it as you're forced to this week and in future weeks. Okay. And, in reality, uh, did, did you wait just a second? Let me check on that. Don't go anywhere. Stay right there. Okay, you guys still there? Hey, look who's here. It's Professor Math Chicken. Hey, Ariadne. How are you? So, Professor Math Chicken. Yeah. Why are you here for? I want to tell a joke instead of hearing your boring stuff. My boring. Okay, well, fine. You can tell a joke, but I think it's interesting. Yeah. Yeah. Hey, to you. Okay, ready, everybody? Why don't you tell secrets on a farm? You said, why don't you tell secrets on a farm? Yeah, that's what I said. I give up. Why don't you tell secrets on a farm? Because the potatoes have eyes and the corn has ears. Okay, that was really good. I thought so. Okay, well, thank you for coming, Professor Math Chicken. Everybody say goodbye to Professor Math Chicken. And don't go anywhere again. I'm back. Okay, we're back. You ready? Let me go over here. And so let's use a problem where we have to use implicit differentiation. Okay, if I have y, oops, just did that. If I have y squared equals 2, no, we don't want to do that. We'll just do x squared plus 2x plus 5. The evil 2 here is why we have to use implicit differentiation, right? Because it's not for y, it's for y squared. So we're going to go ahead and do that. We go ahead and do our thing, and what we say is we want the derivative with respect to x of y squared, and that's going to be the derivative with respect to x of this other side, the right side, right? Now, notice if you follow normal algebraic rules, the reason we can do that is because we're doing the same thing to both sides. So it's not like we're just doing one side, okay? So now, if we follow the way we're supposed to, we can use the power rule. So we bring the 2 down here, y to the 2 minus 1. Now, we got to use the chain rule. In the inner function in this case, is y. Okay? So now, what is the differential with respect to x of y? Well, that's going to be, of all things, dy over dx. So far, so good? You like that? Okay, now on the right side, it's simple. You're used to this stuff, right? So you're going to say, oh, that's just 2x plus 2. Boom, you're done. Well, we want to get this alone. That's what we're trying to figure out overall. So what do we have to do? Well, let's go ahead and simplify this. This is 2y to the 1, right? So that's 2y dy dx equals 2x plus 2. Then we're going to divide both sides by 2y. And then we end up with dy dx equals 2x plus 2 over 2y. Are we done? We done? No, we are not done. We have to divide by 2, so we get dy dx equals x plus 1 over y. And we box it, and we say answer, and we all celebrate. Right? Okay, we got that. So, how does that help? Well, that's a simple one. Let me show you how we used the chain rule with that, because technically when we did the implicit differentiation, this was a chain rule, inner function, chain rule, right? Inner function, chain rule, okay? So let's say we have the more simple one. Let's say we just had y equals x squared plus 2x plus 5. How are we actually doing that? Well, let's think about it. Let's write it out like we did the top one. We're going to just say d, the derivative with respect to x of y, equals the derivative with respect to x of x squared plus 2x plus 5. So far, so good? Okay. Now, we're going to do the same thing. This, by the way, wouldn't this be y to the 1? Do you allow that to me? Okay. So we're going to go to take this derivative. We're going to bring the 1 times y, and then we're going to go 1 minus 1, right, using the power rule. And then, again, this is our inner function. Y is our inner function. So we need to do the chain rule, and we take the derivative of y, and we get dy dx. See what's going on here? Okay, what about the other side? Because we're actually using the chain rule technically with it too. You may not realize it. So now think about this. We know we can break out these into their components, right? So the first one, we're going to have 2x using the power rule. That'll go to the 1. And then if we treat this as the inner function of that one, x as the inner function, that would be dx over dx, right? Taking the derivative of the inner function, and we're treating x as the inner function, right? So in essence, x squared, right? And then we do the next one, and we have, it's just 2 because it becomes x to the 0 using the power rule. But again, if we treat x as the inner function, then it's going to be dx. And of course, 5 is going to be 0 plus 0, right? So now this looks a little messy, but think about what happens here. We have 1, right, times y to the 1 minus 1 is y to the 0, dy dx equals 2x times dx would be 1, wouldn't it? Plus 2 times dx would be 1 plus 0. Well, y to the 0 is 1, so we have 1 times dy dx. So we have dy dx equals 1 times 2x is 2x, plus 2 times 1 is 2. And look at that. So basically, yes, you wouldn't want to do it this way because it'd be complicated, but you've been using the chain rule and you've been using implicit differentiation from the beginning. You just kind of mentally or I guess stepwise skip things, but you've been doing it. And you would have immediately said y equals, if I gave you y equals x squared plus 2x plus 5, and I said find dy dx, you would just immediately have said dy dx equals 2x plus 2, right? But that's the magic behind it. So I don't know if this is helping. If not, I apologize. Hopefully, if it's not helping, if it started confusing you, you immediately turn it off. So I'm not going to watch the rest of this. But hey, this is why I love calculus and stuff. It all hooks together. And, I think this started hitting me when I went through Calc 1. And it just, as I was studying 3.7 and 3.8 in our calculus book this week to prepare for the supplementary instruction sessions, it was reiterated to me, and I was hoping to show you in an SI session, but you all didn't show up. We'll be here Thursday to show you in a SI session. But there you go. You've been doing it all along, so don't let it get you all freaky deaky. I mean, final comment is what you are doing. You saw this last week. You'll see this week, and you go in future weeks. A lot of what you're doing is you're being given tools, and then you're being given practice so that you know how to use the tools in complicated ways. And they will give you messy equations. I hated it when I was going through really messy equations where you'll have to do chain rule on chain rule, and you'll have implicit differentiation where the algebra is not near that simple as dividing by 2y. But it's so that you're not only comfortable with the rules, but you know how to use them in complex situations without dropping signs and dropping components of equations and stuff. But either way, my name's Alan Farner. If you happen to see this outside of the class, don't hesitate to contact me. Farner, AFAHRN as in Nancy, ER at iu.edu. I love math, even if you're not one of the classes that I do supplementary instruction leadership for, I'm more than glad to see if I can help you out. See you guys later.